Hello, welcome to 5G QoS course. I'm Puri Alinejad, and during this COVID-19 pandemic, I had the opportunity to record this video on 5G QoS for you, and I hope that you like it. Currently, I'm working as a Technology Roadmap and Solutions Engineer at MCI, and as you may know, MCI is the biggest mobile operator in the Middle East. Previously, I was with Huawei as a BSS engineer, so basically I know myself as a radio access network engineer. But due to my responsibilities at my current job at MCI, which involves investigating end-to-end network standards and running various testbeds and trials in order to test new technologies like 5G in our network, I'm also involved with end-to-end network concepts. And this QoS in 5G is also an end-to-end network concept, and I am going to share the knowledge with you in this video. I don't have long to talk, so I cut to the chase. My contact detail and my CV and my information is always available at this link, www.palinejad.ir, and in case of any questions, you can contact me on LinkedIn account, linkedin.com in Puri Alinejad. So let's start the course by looking at its agenda. I also closed this webcam window so you can concentrate on the contents. Okay, at this course, I will discuss 3GPP standards on 5G QoS, and I also added a short description of 4G QoS for review and comparison. At the first section, at background, you see with 6 slides, I will lay the ground for getting into 5G QoS concepts. Then, in second section, I will briefly discuss 4G QoS mechanism, and we will see how 4G terms are changed in 5G. Then, a list of standards on 5G QoS is listed in section 3. Then in section 4, we will dive into the details of 5G QoS architecture, and afterwards in section 5, I will describe 5G QoS flow characteristics. Then the 6th section is a little bit more sophisticated, and we will talk about QoS provisioning in 5G and also QoS mapping, and how 5G core elements cooperate in order to map QoS to 5G flows. So we will see mapping, enforcement, and provisioning in this chapter. So next, move to the next slide. At section 7, I will talk about some remained yet important topics related to QoS, like STAP layer. STAP is a new layer in 5G. It wasn't available in 4G. NB-IoT QoS in 5G, and QoE term, and some examples to show how all previous concepts in previous chapters work. And finally, I will conclude the course in section 8 and references. References is not a separate chapter, and I put references at least in the bottom of every slide. So if you see the bottom of every slide, you will see the reference, and you can refer to the main document if you want to read more. Okay, here we are at, let me choose the laser. Okay, here we are in the background section, chapter 1. And if you are looking for pure technical stuff, you should follow this section until we start the next chapter. At the first slide, we look at the reason why QoS is useful for telecom operators. In this picture, you see that operators can move in 3 main directions in their corporate level strategy in upcoming years. Currently, they are providing basic connectivity, and they should seek ways to gain incremental value from basic connectivity and what they currently can offer by their network. This includes voice and data and, for example, basic IoT. In the first direction, in beyond connectivity, operators will develop new solutions, sell more third-party products, sell more third-party services, sell more third-party solutions, and develop platforms for APIs. Then, in the second direction, they can offer managed solutions and connectivity plus solutions. This is possible by applying data science and AI tools to IoT customer data. For example, an operator can help the fleet management company to identify new business opportunities or more efficient ways of running their business. Differentiated connectivity is the third direction, and it is about QoS and it is our interest in this course. So by offering a customized connectivity, operators can better monetize connectivity and raise their income. And with this, operators seek to offer different quality of service to different customers at different price levels. So here we see the answer of why QoS is important. It is about money. So let's see the next slide. Since the early 1970s, both fixed and mobile operators have tried to offer this QoS, this differentiated connectivity to enterprise customers. This table is a brief review of 15 differentiated connectivity capabilities that have been introduced in telecom industry since 1974. Several of these technologies like leased lines and ATM have been marketed to enterprises for several years, and however, now we must consider that there also have been challenges in selling differentiated connectivity, and right now enterprises already indicated that there is not enough clarity on 5G proposition. So we as operators have to be completely clear that there are specific problems that we are solving, specific business problems, not just infrastructure and network problems. Okay, I don't know that you see this window recorder software window, but I hide it so it doesn't shadow the slides. In this image, in this slide, we see 4 business models for cloud augmented reality, virtual reality in 5G era. In the first column, we see subscription-based model in which user pays by subscribing to the VR platform provider. And then in the second section, in the second column, user pays per download or per view. These two models are familiar to us, and we buy internet subscription from our ISP in one of these two models. The third column is ad funded, and you see the term CPM based payment here, and CPM is abbreviated form of cost per thousand, or also called cost per mile. It is a marketing term used to denote the price of 1,000 advertisement impressions on one web page. For example, if a website publisher charges $2 CPM, it means that the advertiser must pay $2 for every 1,000 impressions of its advertises. So here the subscriber watches through VR platform, but advertisement company pays for the VR platform usage. Now let's take a look at the last column, which shows differentiated pricing. differentiated pricing. I also had some animations, but I forgot to click on it. Okay. The last column is differentiated pricing. It means uplink and downlink and latency is guaranteed by operator, and user pays for differentiated service. So while subscriber uses VR platform, he is assured that he have minimum requirements for a smooth VR experience. So in this case, we are selling the differentiated connectivity. Okay, here we have IMD 2020 requirements for 5G, and we will take a look at these values now, and later we will see how 5G QoS indicators are defined by 3GPP to support these values in network. As you can see in the fifth row, latency in user plane is required less than 4 milliseconds, and reliability is 10⁻⁻5 for a special PDU, 32 bytes within 1 millisecond. So here we have some simple topics just to review what we currently know, and these are the factors that affect the network service quality, and we need to be informed about them. We need to learn about them to be able to improve network quality. Traditionally, these factors that affect network quality include link bandwidth and the packet transmission delay. I can mention some important delays like processing delay, queuing delay, serialization delay. And next one is jitter, and at last, packet loss rate. To improve the network service quality, we need to ensure the bandwidth of transmission links and reduce packet transmission delay and reduce jitter and packet loss rate. The acceptable end-to-end delay for voice over IP is about 150 to 200 milliseconds, so the jitter for VoIP packets must be limited so the buffers at the receiving end do not become exhausted, which breaks up the audio flow. On the other hand, we have file download from FTP site that doesn't have such stringent delay requirements, and jitter does not impose a problem for this type of application. As another example or another ways for reducing jitter, we can increase link bandwidth or prioritize delay sensitive packets and forwarding important packets first, or do layer 2 payload compression, RTP header compression to reduce IP packet size and send the packets in a proper way which is effective for VoIP traffic. These factors that affect the network service quality become QoS indicators, and we will see them in standardized charts later. And another topic which is important to review before starting pure technical QoS slides is QoS models. The question is, how are QoS indicators defined within proper ranges to improve network service quality? The answer is using QoS models. The QoS model is not a specific function, but it's an end-to-end QoS scheme. It means, for example, we have intermediate devices between two connected hosts, Let me draw two hosts and the intermediate devices. See here, for example, we have one host and one another host here, host number 1 and host number 2. And of course, in this cloud between these two nodes, we have some intermediate devices. Okay? This QoS model means that if we want to guarantee end-to-end QoS between host 1 and 2, all intermediate devices should use or must use the same QoS model as host 1 and host 2. For example, if host 1 and host 2 are using differentiated service model, all intermediate devices should and must use the same model. And during last decades, international organizations such as IETF and ITUT designed QoS models for their concerned services. Let me clear this shape and reselect the laser point. Okay. Here, the first and simplest model is best effort model, and it is simply a network without QoS. This model treats all packets equal, and all packets are equally important. This is the default service model on the internet and applies to various network applications like FTP and email. Then, in this best effort model, an application can send any number of packets at any time without even being approved by network or without even notifying the network, and then the network tries and makes its best attempt to send the packets, but unfortunately it does not provide any guarantee for performance. So this is not a proper model for QoS. So the first attempt to standardize QoS came in the mid-1990s when IETF released Integrated Service RFC, which was centered on a resource reservation protocol. Integrated Service, also known as hard QoS, is an absolute reservation of services. In other words, the integrated service model implies that traffic flows are reserved explicitly by all intermediate systems and resources. For example, here you can see that the source sends signals and it needs 2 megabit per second. It tells every node that I need 2 megabit per second. And the destination node confirms, and all intermediate devices confirm, okay, we reserve 2 megabit per second. This RSVP requires every node to reserve resources. This is highly impractical in networks with servers, switches, and routers from multiple vendors. And therefore, to address this challenge, the differentiated service model emerged. This model classifies packets to differentiate them, and an application does not need to apply for network resources. An application doesn't need to tell every node that I need 2 megabit per second in priority, but it just notifies the network nodes of its QoS requirements by setting QoS parameters in its IP packet headers. Therefore, compared with integrated service model, differentiated service model requires no signaling. In this differentiated service model, when traffic congestion occurs, classes with higher priority are given preference. This allows packets to be differentiated and to have different packet loss rates, different delays and jitters, and this is what we are chasing in QoS enforcement. Here you see that in this case we have a differentiated service domain and packets are classified upon arriving on the boundary, and resource allocation and traffic control is based on the marker on the interior node. Also, some mechanisms in the differentiated service model is mentioned, like traffic classification and marking, traffic policing, traffic shaping, interface-based rate limiting, and congestion management and congestion avoidance. And you can search online to find out more details on them, and I'm not going to be specific on them because they are not all about 5G, they are basic QoS concepts. Next, move to the next slide. This was the end of background overview. I hope that you liked it. In the next section, we will have comparisons for 4G and 5G QoS in 7 slides. QoS mechanisms offered by 4G. In order to start the comparison, let's take a look at this architecture, 4G QoS architecture. As you know, the 4G system is a connection-oriented transmission network, which requires establishment of a logical connection between two endpoints, for example here between UE and P gateway. This logical connection is called EPS bearer, and to each EPS bearer is associated a radio bearer, an S1 bearer, and an S5 and S8 bearer. We are just reviewing 4G concepts. If you know this, you can simply skip these slides until you arrive to the 5G slides, but we are just looking at a helicopter view to these parameters. Now we know that LT bearer is a transmission pass through the radio interface and the infrastructure with a defined capacity, latency, and packet loss. And the QCI, QoS class identifier, are transmitted between network nodes and they specify requirements for priority, packet loss, and delay. 5 primary QoS parameters that could be determined for the EPS bearer in 4G are listed here. Allocation and retention priority, ARP, is the priority of EPS bearer during resource allocation, and based on ARP, the E node B decides whether to accept or reject a bearer establishment or modification. I'm not going to be specific on these parameters, guaranteed bitrate, maximum bitrate, aggregated maximum bitrate, but I will discuss details of same parameters in 5G in subsequent slides. This figure shows downlink IP flows. Here you see downlink IP flow 1, 2, 5 delivered to a UE. Here we have the UE through EPS bearers and also SDFs. These SDFs are classified using SDF templates and TFTs, traffic flow templates. These SDF templates are kind of packet filters. The IP flows which arrive at a P gateway from this PDN are filtered by SDF template to SDFs. Here IP flow 1 and 2 and 3 are filtered to SDF 1 and 2 and 3, and you can follow them by their color. Okay? Here the IP flow 4 and 5 are mapped to SDF 4. The differentiated QoS policies are applied to each SDF, which is classified by this TFT, and then SDFs are mapped again to bearers. Here the SDF 1 and 2 are mapped to the default EPS bearer, and SDF 3 and 4 are mapped to dedicated EPS bearer. All destinations are toward the UE, and upon arrival to the UE, all flows are IP flows are mapped to their corresponding applications. Here you can take a look at 4G QoS provisioning. I'm not going to discuss it a lot because it's again 4G concept. You see here orange boxes are provided by HSS and PCRF can modify them. Blue boxes are provided by PCRF and brown box is provided by HSS, and MME can of course replace the UE AMBR by the aggregated set of AP and AMBRs, and we know that the UE AMBR cannot exceed the value that is preset in the HSS, so that value in HSS is the upper bound for UE AMBR. This is the last slide on 4G from netmanias.com. Sorry. By the way, all my slides have references at the bottom of the page, and if you need to read more, you can refer to the main documents. Here we have UE, two P gateways, P gateway 1 and P gateway 2, two PDN connections, PDN connection 1 to UE and PDN connection 2 to the same UE. And we have two default bearers for each, one default bearer for each connection. Overall, we have two default bearers and they are non-GBR, and we have dedicated bearers. One of them is GBR and one of them is non-GBR. And in case of GBR, you see that we have extra parameters, GBR and MBR, in QoS parameters of EPS bearer and also QoS parameters of SDFs. So overall parameters of EPS bearer include QCI, ARP, GBR, MBR, and in case of non-GBR, we have UEA MBR and APN AMBR. And you see the UEA MBR is the aggregation of all APN AMBRs on all PDN connections of the APN connection on the UE. And overall, the QoS parameters of SDF are QCI, ARP, MBR, and GBR. Here, let me bring one example of the bearer establishment. Here you see that we have a bearer which is GBR is 2 megabit per second, and currently it supports to handle SDF3 with 1 megabit per second GBR and SDF4 with 1 megabit per second GBR. So overall it is 2 megabit per second, and this EPS bearer is completely occupied. If another SDF arrives, for example, with GBR 500 kilobits per second, then the P gateway keeps traffic mapping between the TFT filters, and it is responsible for the EPS bearer and SDF mapping. And here the P gateway knows, okay, this EPS cannot handle extra SDFs, and this SDF should be mapped to a new EPS bearer, and a new bearer will be established for this new SDF. Now we are ready to see the first slide on 5G QoS. This is the QoS architecture for 5G, and as you know, NG-RAN is the new RAN in 5G. We have UPF for user plane traffic in core side. AMF and SMF are not shown in this image, but they are handling tasks offered by MME in 4G. Also, I added here that N3 here, N3 interface is between NG-RAN and UPF, and N9 interface is the interface between two UPF, and their protocol is GTP. In 5G, the QoS framework is based on QoS flow, and here you see the QoS flow, and it is at NAS level. And what is exactly written in 3GPP standards is at NAS level, it is the finest granularity of QoS differentiation in a PDU session. It means the QoS parameters and QoS characteristics are tied to a QoS flow. So we don't have bearers, and instead we have flows. Again, we had same image for 4G. You can see it here. This one. And I'm going to repeat this image for 5G, and let's see how things change. Okay, now you see it's easier to understand this image for 5G. Same IP flows are mapped using TFTs to SDFs, and these SDFs, which are now classified, are mapped to QoS flows by UPF. In 4G, this mapping was P gateway task. Please note this part, this is important, and this is the first change between 4G and 5G in QoS. As you see, after mapping here in UPF, there is another mapping in GNodeB to DRBs. This was not available in 4G, so mapping is 5G is implemented in two steps, once in UPF and once in GNodeB. And the GBR and non-GBR terms here, GBR and non-GBR terms, are repeated from 4G, but there are some new terms like QFI and SDEP, and I will discuss them in more detail later. Okay, these are more detailed information and we will discuss them in next chapters. Here we have a table with 4G and 5G QoS parameters. In first row, QoS identifiers in 4G are called QCI, Quality Class Indicator, and in 5G they are renamed to 5QI, 5G QoS identifier. In second row, the concept of QoS is in LTE is based on bearers, and the concept of 4G is based on flows, so we have QoS flows. In the third row in 4G, EPS bearer ID or EBI is used to distinguish between different quality of services, while in 5G it is identified by QoS flow ID, QFI, or QoS flow identifier. So each flow has a separate QFI. 5G also introduces a new concept, reflective QoS, and it was not available in 4G. We have some slides to see what this new feature is, and in a nutshell, it is QoS enforced by UE in uplink direction. But wait for next chapters if you are curious about it. Okay. Now in next section, in next chapter, in chapter 3, let's see the list of standards on 5G QoS, and then we will dive into details in the subsequent chapters. QoS topics in all these standards, the standards that you see here, are discussed in the rest of this course. Most of the contents are from this document and also this document, and the rest are mostly cross-referenced to other documents. So let's move on and go to next slide. Here we'll start the 5G QoS architecture chapter with 6 slides. We've seen a more detailed picture in previous chapter, but here I will add notes step by step to this simple architecture. We know that a PDU connection establishes in 5G between UE and UPF. And for each UE, 5G core can establish one or more PDU sessions. Here we just have one PDU session. The first thing to consider is that NGRAN can establish a data radio bearer for each QoS flow, or may combine several QoS flows on a data radio bearer. It is based on the logic in the NGRAN. It is based on NGRAN when to do so and create new DRB for new QoS flow. It means that there is no strict one-to-one relationship between QoS flows and data radio bearers. The optimization of this mapping is not included in a standardization, and it's up to vendors to do this optimization. Also, please note that this information may change in case of NB-IoT in 5G, and UE and NGRAN may have different behaviors then. I will discuss NB-IoT case in a separate slide at the end of the course because it contains some exceptions. We have same image here, but this time we have 2 PDU sessions. In previous image we had just 1 PDU session. And QoS flows, we have here the QoS flows and 2 QoS flows in one DRB and 1 QoS flow in the other 2 DRBs. The next point is each QoS flow is identified by QoS flow ID, QFI, and it is unique within a PDU session. So we have QFI for QoS1 and another QFI for QoS2, QoS flow 2, and so on. The user plane traffic with the same QFI in a PDU session receives the same traffic forwarding treatment, and treatment here means having different scheduling on that flow and having different admission threshold or same admission threshold and same scheduling. And as we have seen earlier, this 5G QoS model supports both GBR and non-GBR QoS flows. And again, I repeat here that NGRAN and 5G core ensure quality of service by mapping packets to appropriate QoS flows and data radio bearers. So we have 2-time mapping, and the first one is NAS and the second one is access stratum. The next point is QFI is carried in a GTBU encapsulation header on N3, and in case we have 2 UPFs on N9 interface. And the thing that remained is Qos Profile and 5QI. 5QI is defined as a part of Qos Profile, but let me at first define the term reflective QoS because we need to know reflective QoS parameters in order to understand Qos Profile parameters. So let's start talking about reflective QoS first, then I will talk about and discuss about Qos Profile after that. Reflective QoS. In previous chapter, we see a new term reflective QoS, which was not available in 4G. The concept of reflective QoS, here you see, was developed to minimize the need for NAS signaling between the UE and the core network when enabling QoS differentiation. So the goal is to reduce nest signaling. This reflective QoS means that the mirrored data packet is getting the same QoS treatment as the received data packet. In other words, when reflective QoS, or abbreviation form of it is RQ, is enabled for QFI, for example here QFI 3 have enabled reflective QoS, the UE creates derived QoS rule. So UE knows that there are some reflective QoSs, and when this flow arrives to the UE derives the QoS rules. And data classification based on this downlink packet will be down on the uplink direction for the same QFI. So in uplink direction, UE will find the matched QF rules in its list of derived QoS rules. If the same QFI is founded, then it will apply same QoS to the uplink direction. For example, if we have here a QFI 4, the UE says that it doesn't have derived QoS rules for QFI 4, so it will send it as a normal packet, but for QFI 3 it will use the reflective QoS parameters. And this reflective QoS can be enabled for PDU sessions with IPv4, IPv6, IPv4v6, or even Ethernet PDU session types. And especially it is useful for applications which frequently generate data packets with different header values. Okay, if header values are changing, then we would have so much nest signaling, and our aim was to reduce nest signaling. For example, HTTP traffic generates new port numbers, and in order to avoid nest signaling for updating the UE for each port change, we can use reflective QoS. Okay, we have a sentence here, but it's hard to understand it now. Just read it once and we will be back after checking the procedure in the background. Just read it once and later, after checking the procedure in the background, it will be easier to understand all these new terms. The reflective QoS is controlled by the 5G core 5GC on a per packet basis by using the reflective QoS indication RQI in the encapsulation header on N3 and N9 reference point together with the QFI and a reflective QoS timer, RQ timer. Okay, now let's see the procedure. Here we have UE 5G access node. This is the G node B, AMF, SMF, UPF, and PCF. This UPF is responsible for the user plane traffic, and the others, AMF and SMF and PCF, are signaling and control plane layer. Okay, in part A here, the UE indicates that it supports reflective QoS and is down during the PDU session establishment or modification. And this, for example, PDU session modification can happen when the UE moves from EPS to 5G core during a handover from 4G to 5G on N26 interface. And if you are not familiar with N26 interface and the procedure for PDU session establishment and modification, you should see some courses for 5G network architecture, and these are elementary 5G concepts. So here UE tells the SMF that, hey, I support reflective QoS. Then in section B, if SMF determines that the reflective QoS is to be used for a service data flow, SDF, for a specific QoS flow that the UE requested, The SMF provides the RQA, and it gets the RQA from PCF. Okay, so SMF downloads the required information from PCF, required instructions from PCF. And then in section C, when UPF receives an indication it received in the previous section in B, UPF is now aware that some special flows need some special reflective QoS. Now the UPF needs to apply it. So UPF should set the RQI value in the encapsulation header on entry interface, entry reference port, for every downlink packet for that service data flow. Then when the RQI is received by the 5G access node or NG-RAN in downlink packet on entry reference point, the 5G access node indicates the UE, the QFI, and the RQI, and the data also, of course, and the NG-RAN uses the step layer. Step layer, as I said earlier, is a new layer in G-Node B, and we will talk later about it. For the G-Node B uses the step for the RQI and QFI information. It retrieves this information using step layer. And now let's back to the sentence and read it again and see if it makes sense now. The reflective QoS is controlled by 5G core on a per packet basis. Okay, here we see that these elements are from 5G core and they control the reflective QoS. By using the reflective QoS indication, RQI, and here we see that UPF sets the RQI in entry encapsulation header, or maybe N9 in case we have two UPF, together with the QFI. Here we also have QFI and a reflective QoS timer. Okay, now this sentence is okay. You just didn't see a reflective QoS timer. So for this one part, reflective QoS timer, let's go to the next slide and see what it is. In this slide, we have enabling procedure. We have controlling procedure. In previous slide, we had enabling reflective QoS, and here we have controlling reflective QoS. And controlling means that after the reflective QoS enabled in previous slide, here we have the remainder sections D, E, and F, and G, and to close the reflective QoS feature here, the UPF, SMF, and PCF, AMF, and 5G AN send signals to close the reflective QoS, and then at the end there is a timer. If the timer expires, RQ timer expires, UE removes UE derived QoS rules. So all the derived QoS rules for reflective QoS are freed after this timer expires. So in this sentence, now you know the reflective QoS timer is used to finish the reflective QoS feature. Now it's time to go back to QoS flow characteristics. You remember before reflective QoS we talked about QFI, and here we are going to describe QoS profile. You see here, let me go back. Here I told that there is QFI in each flow, and there is also QoS profile and 5QI in each flow, but I didn't discuss them. I told that at first I will discuss the reflective QoS and we will back to QoS profile. Now it's time to go back to QoS profile. Here, let's go back to QoS profile and see what is it. I mentioned RQ reflective QoS earlier, because in QoS profile we have terms that need RQ concepts to be known at the first step. Okay, here at NAS level, a QoS flow is characterized by a QoS profile provided by 5G core to NG-RAN, and also a Qos rule or Qos rules provided by 5G core to UE. So the Qos rules dictates the mapping between uplink user plane traffic and Qos flows to the UE. So Qos rules are for UE, and the Qos profile is used by NG-RAN to determine the treatment on the radio interface. So Qos profile is for NG-RAN and Qos rules are for UE. And Qos profile can be GBR and non-GBR. Okay, till now we know something about 5G architecture, and now we need to go into the details of this architecture and see the characteristics in more details. What is the exact parameters in the Qos profile? In this section, we are going to discuss these things. So let's check the Qos rules, because it have less content than Qos profile. Qos profile have a lot of content to discuss, but Qos rules is just this one slide. And in next slide we will talk about Qos profile comprehensively. The UE performs the classification and marking of uplink user plane traffic. It means that the association of uplink traffic to Qos flows based on Qos rules. As I mentioned in previous slides, Qos rules are for UE to adjust uplink traffic Qos. Okay, it's easy. But this classification and marking is done in two ways. Here we have two ways. Whether it is implicitly derived by the UE by applying reflective QoS, we see that we can enable reflective QoS, and UE can derive the required QoS parameters by getting the RQA and QFI, or by NAS. The NAS protocol enables the network to provide the UE with signaled Qos rules associated with the PTU session. So UE can get them by NAS signaling. Each signal Qos rule contains these parameters. So these are the building blocks of Qos rule. An indication of whether the Qos rule is the default Qos rule. Here we may have some default Qos rule or maybe some later configured Qos rule. A Qos rule identifier, a Qos flow identifier, we will talk about these later. Optionally, a set of packet filters, and it varies for uplink, downlink, and scenarios for default or non-default Qos rules. And a precedence value. Now we must get ready to study Qos profile parameters. But at first we need to know some definitions. We need to have some dictionary. The first one is guaranteed flow bitrate, GFBR, and it applies in downlink and uplink. It reminds us to GBR term in 4G. The same applies for MFBR. MFBR here. We had same for 4G MBR, and we know that for MFBR, excess traffic may get discarded or delayed by a rate shaping or policy function at the UE, RAN, or UPF, and is same as 4G. The next term is Qos notification control, and this Notification control can be requested from NGRAN when the GFPR cannot be fulfilled. And if this GFPR cannot be fulfilled for a QoS flow during the lifetime of this QoS flow, then the NGRAN shall notify that something happened to a special flow and I cannot guarantee the flow bit rate. This definition is a bit vague and unclear, so let me explain it more. QoS notification control, and its abbreviated form is QNC, shows if RAN must send notifications when the GFPR cannot be satisfied, or again can be satisfied after, for example, a RAN congestion or radio link failure happens for a QoS flow. So by any change on GFPR status, NGRAN shall send notification and sends them to SMF to inform it that the GFPR can be guaranteed again, and also the SMF may forward the notification to the PCF. The next term is maximum packet loss rate. And for maximum packet loss rate, we have seen in previous slides that packet loss rate is an QoS indicator. If I go to the slide, it was in the first slide here, you see that the packet rate loss was a QoS indicator. And here, in our slide 33, here now you see that it's a part of QoS indicators. The packet loss rate is an QoS indicator, and here we see it's defined, and in next slide we will see it as a part of Qos profile. It indicates the maximum rate of lost packets which can be tolerated for a specified Qos flow. The reflective Qos attribute indicates that a certain traffic for a specified Qos flow can be subjected to reflective Qos treatment. So let's back to previous slide and import, I think it was B of procedure. Here we had the RQA to indicate that this flow or this specific QoS flow can be subjected to reflective QoS. Okay, let's go forward. And this was just these definitions. You need to know them in order to better understand the remaining sections. Now we are ready to see all Qos profile containments completely. Now we know about reflective QoS, and now we know the dictionary terms. In previous slide we know some terms, and here let's read it. For each Qos flow, the Qos profile shall include these Qos parameters: a 5G QoS identifier, 5QI. We know in 4G it was QCI. An allocation and retention priority. We had the same value in 4G. And if the flow is GBR in the left box, if it's GBR, here we have the shown parameters shall be included: guaranteed flow bit rate, maximum flow bit rate bus for uplink and downlink. And we already seen the definitions of these terms in previous slide. And some parameters may be included, like the maximum packet loss rate, delay critical resource type, and notification control. And this delay critical resource type is maybe for URLC, ultra reliable low latency use cases. And in case of non-GBR QoS, we need to have 5QI ARP and reflective QoS attribute RQA. and some additional QoS information. This additional QoS information is listed in the standard, and they may be vendor specific, but for example, in GBR case, we can add optionally an EPS bearer identity, EBI, in the QoS flow, if it can be mapped to EPS. Okay, let's see more details about first parameter 5QI in next slide. 5QI and its characteristics. Now we know 5QI is a part of Qos Profile. For each Qos flow, if we want to set node-specific parameters, then the 5G Qos characteristics should be understood as guidelines. For example, 3GPP radio access link layer protocol configurations need these characteristics and terms to be configured. This table shows 5G Qos characteristics for 5QI. Here we have all of them. The characteristics describe the packet forwarding treatment that the Qos flow receives edge-to-edge, end-to-end between the UE and UPF. The first one is resource type. The resource type can be GBR or non-GBR or maybe delay critical, GBR resource type, and these are all three resource types that can be associated with a flow. The next one is priority level. The priority level as the 5G Qos characteristics indicates a priority in scheduling resources among Qos flows. The lowest priority level value corresponds to the highest priority. The next one is packet delay budget, PDB. And the PDB defines an upper bound for the time that a packet may be delayed between UE and UPF. And UPF terminates the N6 interface, and if you want to see it here, refer to this architecture of 5G reference architecture of 5G. You see UPF terminates the N6 interface and is connected to RAN using the N3 interface. Again, if you don't know these things, you should see a course on 5G architecture at first. And now you know that packet delay budget is calculated from this UPF to the UE. The next one is packet error rate, PER, and it defines an upper bound for the rate of PDUs or the IP packets. And these IP packets have been processed by a sender of a link layer protocol like RLC, but they are not necessarily delivered to the corresponding receiver of the upper layer, for example, the PTCB layer. So packet error rate defines an upper bound for a rate of non-congestion related packet losses. And the losses are happening between RLC and PTCP. And the purpose of PER is to allow for appropriate link layer protocol configurations, for example, RLC and HARQ in RAN. And for every 5QI, the value of PER is the same in uplink and downlink direction, so we don't have separate values in uplink and downlink direction. And for GBR Qos flows with delay critical GBR resource type, a packet which is delayed more than PDB, more than this PDB here, is counted as lost and included in the PER. The next one is averaging window. Each GBR Qos flow needs an averaging window. The averaging window represents the duration over which the GFBR and MFBR are calculated. We need a window to calculate these values. The maximum data burst volume MDBV. If we have a GBR Qos flow with delay critical resource type, it should be associated with a maximum delay burst volume MDBV, and this denotes the largest amount of data that the 5G access node or NGRAN is required to serve within a period of 5G access node PDB. And don't worry, you will see it in next slide and it will be clear there. Okay. Here we have 5 Q values table in the standardization. And also I added the same table for 4G QCI values for comparison here. So we have 5 QI values for GBR resource type, then 4G GBR resource type, then in next slide non-GBR in 5G and non-GBR in 4G, and then delay critical GBR in 5G, and we don't have delay critical in 4G, but it is defined in a standardization as GBR, but the parameters are same as the delay critical GBR, but it's named again as guaranteed bit rate. So let's back to the next slide. So we have 3 slides for 5Q values, GBR, non-GBR, and delay critical, and we have 3 slides for 4G GBR, non-GBR, and also again GBR, which is equivalent to the 5G critical GBR values. And here you see that we have the terms that we discussed in previous slide: resource type, default priority level, delay, packet delay budget, PDB, packet error rate, default maximum data burst volume, default averaging window. And here you see example services. For example, for mission critical video on user plane, we have 10 power minus packet error rate, while for something like conversational video live streaming, we have again 10 minus 3. For conversational voice, we have 10 minus 2, and packet delay budget varies among them. And the priority level also varies, and we know from previous slide that lowest priority level value corresponds to the highest priority. So the lower the value, the highest the priority is. Here, the real-time gaming has higher priority than conversational video. And another important thing to consider here is packet error rate in 5G, which was mentioned in 4G as, I think that my presentation slide freeze. Let me go to next slide. Okay. The packet error rate in 5G is mentioned as packet error loss rate, PELR, in 4G. So here we have a loss more. Packet error loss rate in 5G, it was packet error rate. And the difference here is maybe due to the definitions in the technical specification TS25.301, in which the packet error rate calculation in 4G, which is named packet error rate, error loss rate, is calculated between losses of SDUs, service data units, which are inputs to a layer, but after adding a header, concatenation with a header, it will be the output of a layer, which is a PDU, packet data unit. And in 5G, the packet error rate is calculated based on PDUs, the whole packet. But in 4G, it was packet error loss rate. It was just calculated based on the SDUs, inputs to the layer. And I think in simplified terms, these are just non-congestion related packet losses, and they are intended to capture the failure of the air link and its lower layer retransmission protocol, and just this little bit difference is between 4G and 5G. Also, if we see here the 5QI values 1, 2, 3, 4, 65, 60, 7, and the rest, and default priority levels 20, 40, 30, and the priority levels of the same QCI values in 4G. For QCI 1 we have 2, for QCI 2 we have 4. We see that it is exactly multiplied by a factor of 10. You see here for QCI1 we have priority level 2, and for 5QI1 we have priority level 20. For 5QI, for example, 72 we have 56, but in 4G, it is 5.6. It's divided by 10. And this is simple and greatly expands the range of possible values for future. And 3GPP in this case seems to do a very complete job of transitioning the network end-to-end QoS scheme from 4G to 5G. And you see it here that the mapping is really easy, and other factors like packet delay budget and packet error loss rate are quite the same. And in future, maybe for QoS mapping between 4G and 5G, we will have a simple job. The last point to consider is, I think, on this delay critical GBR, which is new, and its 5QI value is 82, 83 till 86, and its packet delay budget is so stringent, it's tight, 5 milliseconds, 5 milliseconds. It's hard to have this 5 milliseconds latency end to end. And the services are discrete automation, V2X messages, intelligent transport systems, V2X messages for advanced driving and collision avoidance, platooning with high LOA, I don't know what is LOA, platooning with high level of something, I don't know. I need to check this. A spec, it's related to cars and having them in queues. So just check this tables and the values in services, see the new services and different priority levels and packet delay budgets for different services in 5G. Now, if you are looking the slides till now, you know a lot more on 5G QoS. But still there is a couple of information remained. Let me show you here that there are a lot of slides remained, and till now I captured, I think, about more than 1 hour video. So I upload the rest of the slides in a separate video, and I will look forward for your feedbacks in my LinkedIn account, and also you can contact me with my contact details on my webpage palinejad.ir. And the next chapter in next video will be QoS flow provisioning and mapping and QoS enforcement, and after that another section, another chapter will remain. It is the examples and IoT and other cases. Examples as step NB-IoT, QoS fuzzy slicing, and QoE and conclusion. I will upload these remaining slides in a new video. Thank you for watching.